Japan is one of the most technologically advanced countries. One of its significant achievements is the creation of the world's fastest train. How does the fastest train work, and who is trying to compete with it? Read about it in our video. Imagine a train without wheels. Instead of rolling on the rails, it floats silently from origin to destination without even touching the rails. This may sound like science fiction, but examples of this technology, known as magnetic train suspension, are already being developed in many cities around the world. These futuristic locomotives offer many exciting new travel possibilities. They can become faster, safer, and more energy efficient than conventional transportation systems. Although such trains are still few and far between, they are generating a lot of research in the electrical engineering community. As a result, Maglev may become more commonplace sooner than we can imagine. Maglev, or superconducting magnet trains, are developed by the Central Japan Railway Company back in the 1970s. Maglev trains operate on the principle of magnetic repulsion of the cars on the track. The word maglev itself is a combination of the words magnetic and levitation, and magnetic levitation is achieved by using an electrodynamic suspension system. The rail or rails contain two sets of cross-connected metal coils wound in a figure of 8 to form electromagnets. The train itself contains superconducting electromagnets called bogies. When stopped, the train stands on rubber wheels, the same wheels the train uses to start moving when it accelerates. When the train reaches a speed of 150 km per hour, 93 miles per hour, the magnetic force becomes strong enough to lift the train 100 millimeters, 4 inches, off the ground, eliminating friction and allowing for ever higher speeds. The magnetic force that lift the train also move it forward and keep it at the center of the track. This is the same technology that the Tesla Hyperloop uses. It makes the ride smooth and the train exceptionally safe. Construction and cost of the Maglev project. Plans call for the train to run on the Chuo Shinkansen line, the route between the Japanese capital Tokyo and the large province city of Osaka. The first stage of construction includes about 2/3 of the track to Nagoya and will be completed by about 2027, while the remaining section of Osaka will become operational in about 2045, cutting time travel for passengers by about half to 1 hour and 7 minutes. Initial track construction costs were estimated at an astronomical $100 billion for the Nagoya section alone, with more than 80% of the route expected to pass through expensive tunnels. In 2021, however, Central Japan Railway said that it had learned that the magnetic levitation train project, which would connect Tokyo and Nagoya, would cost an additional 1.5 trillion yen, $13.8 billion. Because of technological problems and the additional earthquake control measures, this would raise the total cost to about 7 trillion yen and create new funding problems in an already difficult time. Additional costs include about 500 billion yen to be spent on ground reinforcement work at Shanghai Station in Tokyo and Nagoya Station. The two terminals that connect the Maglev train, about 600 billion yen, will be spent on reinforcing the high-rise structures on which Maglev moves to withstand strong earthquakes, while about 300 billion yen will be needed to get rid of the huge amount of earth excavated to build the underground line. The high speed of the train means that it needs minimal and relatively small turns, which can also be a limiting factor depending on the location. Problems with tunneling have been a major factor in delaying construction in Japan, along with environmental protests, especially over the tunnel's impact on water levels in local rivers. The financial impact of the coronavirus pandemic has also had an effect on the project's finances, which rely heavily on passengers using the conventional rail system. The top speed is unlikely to be achieved in commercial journeys, which are expected to approach 300 miles per hour, but could still increase in experimental conditions. The latest Japanese Maglev model is the Maglev 10 and was launched in May 2020. It makes some improvements to the power system of the original version, and the train's aerodynamics have also been improved. Now, if the power goes out, the train will just slide to a halt, which has a significant impact on the speed and safety of the train. Designer Motowaki Tarai told the media that the latest version achieves 80 to 90% of the final goals of the train project and, like the earlier version, consists of 12 cars. For now, the train consists of a combination of two different models of old and new cars. Benefits of Maglev. The most obvious appeal of magnet-powered trains is that they can move faster than conventional trains. The lack of friction between the train and the guideway removes many of the limitations that bind conventional trains. There are other equally important qualities that also make maglev attractive. Durability. Conventional wheels and rails are subject to great stress over time. They need to be replaced and repaired periodically to stay functional. With maglev, there is no contact between the train and the rail, so there's much less wear and tear. Because of this, the surface life of maglev elements is much longer than the traditional wheeled trains. Economically, this is a good incentive, since repairs and maintenance are expensive and time-consuming. Safety. It may be counterintuitive, but these trains are safer because they move much faster than their wheeled counterparts. Maglev trains are almost impossible to derail. It takes something like a complete collapse of the tracks to derail a train. In addition, weather is not a big problem for trains because train movement is not dependent on the friction. Snow, ice, and rain have little or no effect. Energy efficiency. Another advantage of levitation is that these trains do not lose energy to friction. This gives them an efficiency advantage. Energy consumption is important to the success of a transportation system since most of the operating costs are spent on electricity. Environmental impact. Magnetic suspension trains can make steeper turns than wheeled trains. This makes it possible to build tracks that will allow much better movement over the terrain. The tracks can be designed to have minimal impact on the environment. Guideways also take up less space than rails. This further reduces the impact on the environment. And, as noted earlier, guideways can easily rise above the ground. Both plants and animals are safer when the train moves over them instead of passing them. Noise pollution. When considering a transportation project, noise, within reasonable limits, is not as important as economy or safety. However, noise reduction is still considered a positive thing. Maglev trains are quieter than modern trains, so this is another argument in their favor. Maglev's critics and competitors. However, experts do not always agree on whether such trains are so versatile, and whether maglev trains could ever replace all-wheeled trains. For example, Deputy Dean of China's Southwestern Jietong University noted that maglev is a great addition to our existing rail transportation. The explanation is that most exciting tracks are incompatible with maglev technology, and maglev trains are more suitable for routes with large numbers of passengers at both ends without unnecessary stops in between. Still, Beijing plans to reclaim its global position as a leading player in an ever-growing high-speed rail network. China's Transportation Power Plan, released in September 2019, included an entire chapter on developing new magnetic suspension lines between its key urban centers. In October 2019, Daily Newspaper reported that tracks will be laid throughout central Hubei province in 2020 to test trains with speeds of up to 1,000 kilometers per hour, based on the theory of high-temperature superconducting magnetic suspension. The state-owned China Railway Group is said to have already completed a feasible study for a new magnetic train network extending from Guangzhou to Beijing. Although the project was temporarily frozen due to the coronavirus pandemic, China's recovery from the crisis has led to the resumption of new infrastructure projects. In late April, Tong Laisheng said that a new version of the train had been tested on the Changsha Maglev Express line. Outside of China, Japan, and South Korea, whose first maglev line connecting Incheon International Airport to Seoul opened in 2016, magnetic levitation technology still does not dominate the market, despite its European origins. Germany had planned to develop something similar with the Trans-Rapid Magnetic Suspension monorail in Munich. However, an accident in 2006 during its testing, which killed 23 people, led to an untimely halt to the project. Another common argument against maglev has always been the financial side of the technology, given that projects have to start from scratch and cannot be integrated into standard rail infrastructure. But despite all the controversy, in early 2021, China showed a prototype of a new new high-speed train on magnetic suspension capable of reaching speeds of 620 kilometers or 385 miles per hour. The train is powered by high-temperature superconductor energy, which makes it seem as if the train is floating on a magnetized track. A streamlined prototype 21 meters, 69 feet long was presented to the media in Chengdu, Sichuan province on January 13th. In addition, university researchers built 165 meters, 541 feet of rails to demonstrate how the train would look and behave on the road. Professor He Shong told reporters that the trains could be put into operation within 3 to 10 years. China is home to the world's largest high-speed rail network with over 37,000 kilometers and the fastest commercial train, the Shanghai Maglev. The country's first Maglev high-speed train started operating in 2003. Its top speed is 431 kilometers per hour. The train connects Shanghai Pudong Airport and Lanyang Street in the eastern part of Shanghai. China is looking to further improve its infrastructure ahead of the 2022 Winter Olympics, which will be held in Beijing. Earlier in the country, an ultra-high-speed passenger express train specifically designed to withstand sub-zero temperatures made its debut. The CR400AFG train can travel at speeds of up to 350 kilometers per hour. It will run on routes between Beijing, Shenyang, and Harbin. The future of Maglev. Maglev technology holds great promise for the development of ultra-fast trains. It has the potential to become a cheaper, faster, safer, and more environmentally friendly mode of transportation than we have today. This technology can be used everywhere, from inner-city public transportation to travel across the country. There are even proposals to build long airless underground tubes and place trains inside them on magnetic suspension in order to eliminate wind resistance and lead to the development of speeds faster than the speed of sound. It may be a long time before this technology becomes widespread, but it's hard to deny that it will definitely become prevalent at some point because its benefits are too hard to ignore. How will all this technology evolve and improve as we move into the future? Time will tell, but it is very likely that we are now on the cusp of a major transportation revolution.